right, while it's going through this medium. And uh, from what I've seen, the description of why this happens is because of the magnetic fields inside of the glass are basically pulling the phase the of the wave back or something along those lines. Like every time the light interacts with an an atom's magnetic field, it's getting pushed back a little bit, right? And I think maybe that's part of it. That might be playing a role, but my problem with that is I was looking at this, right? And so say we have two atoms like this, right? When the light is passing through here, right? This magnetic field will see that as a motion coming at it this way, right? And it would have to react like this, right? But this magnetic field over here, if it reacted like that, it would push it that way. So these would cancel out, right? And they wouldn't have any effect on this overall uh photon of light going through. So I don't think that that is our explanation. I don't think that that's how that works because it should, in theory, not really matter. Because all of the magnetic fields should kind of cancel because there's so many atoms. So for every one that is counter to the photon of light, there should also be one that's beneficial. And maybe I'm wrong on that, but I'm going to move on because um I'm going to show you what I think is going on, right? And so I'm going to draw this larger actually. Let's say that this is our photon of light and it comes out over here. And I want to make this a bigger change. I'm exaggerating this. This is not to scale. And the expected path is here, but it doesn't go that way. It goes like that. And now I'm going to take this to a different subject. And that we have um we know that there's such thing as gravitational lensing, right? So we've got the sun here, and then over here is the earth, and then we'll say this is not drawn to scale either, but then we got like some star out here which looks tiny to us but would actually probably be bigger than the sun, but it's far away, so we're going to make it tiny. And the expected path for this light is to go straight, right? And in theory, the sun's in our way, right? We shouldn't even see that. But we have experimentally proven that we do see it. So what does it have to do? It has to kind of bend around, and it's not a sharp angle like that. It's more of a curve, but I don't know if I can make an effective curve. It would work on this side too. But it's something like this is happening, right? And so um the thing is though, is that when we observe this to us, it doesn't look like it's coming from over here. It looks like it came from over here, right? And so the path that we think happens is it came from over here, went this way, and that's why we see it. But that's not the case, right? The light really it really did just stay straight. It didn't actually need to bend or anything. It stayed on a straight path, but because space-time is curved, it did curve and it ended up kind of looking like this or, bending and making it appear like the light is coming from over in this trajectory. But really, it went straight the entire time. And so what I want to kind of show you here is um if I can highlight just this. which I couldn't. Okay, I see why. I'm gonna draw a new line, and then I will show you what I'm trying to say here. And I think, if you've got an inkling of intuition here, you'll see what I'm about to do. But the expected path of the light, right, is exactly what we see over here, right? So on the giant planetary scale, what we notice is that the light bends, and we call this gravitational lensing. But when we look at it over here, we say, "Oh, that's diffraction." And that doesn't make sense to me. To me, this looks like gravitational lensing, except on a tiny scale. And what's happening is it's also slowing down, right? And why is it slowing down? Well, we know that time moves slower closer to a mass, right? We know that the closer you are to the mass, the time slows down. And so it's not like it's standing in a freeze frame, but the gravitational fields of these particles, although it's extremely small, there's so many atoms in this sheet of glass that it's enough to slow it down, right? And although it continues straight and it doesn't actually bend at all, the space-time around the atoms is bent. And so it gets bent as well. And so we end up with the light coming out over here, traveling a straight path the entire time, but appearing to refract or bend in our eyes. Because gravity is not just effective on the large scale, but also on the small. And basically what I'm trying to show is it looks like we would expect it to have come from over here, right? Like this is the expected path, right? And we know that it did come from over here, but we see it come out over here. So we can kind of do this in reverse. We expect that it would come from over here, travel this way. Like we should expect it to be like this if it's coming out over here, but it's but it's not. There's this bending happening because of all the mass that's in this area. The mass here is causing it to bend. And I mean, honestly, this stuff over here is also causing it to bend. But the point is that um, light doesn't refract because of just the magnetic field. It's refracting because of the gravitational field, because of gravity, because of time distortion, because of space curvature. And so we get this appearing bend in the material, and we've seen it on the larger scale, so I don't understand why it seems so bizarre to observe it on the small. And so I just wanted to kind of put some light on that and bring that to someone's attention because I don't understand why we don't see that already. And we know that the greater the density of the material it's going through, right? The greater the density, the more atoms, that generally the heavier the atoms, the stronger the gravity, right? More mass, more gravity. It moves slower and diffracts more. And a photon of higher energy diffracts less and is affected less because it moves through at a faster rate and is less affected by this time distortion compared to a slower um a slower photon, right? The higher the energy of the photon, the faster it's moving, the less affected by the gravity it is. But this is not this is not what we believe, but I believe it's the truth. And I don't understand why I'm the one that has to say it. Maybe I'm not the first one to say it, but I'm saying it now. So, yeah, that's all. Peace out.